Hello, sir. Hello, sir. Yes, sir.
Okay, how about now? Is it working fine now?
Yes, sir. Now it is
Okay,
fine.
okay, sorry. So I think okay. I think the mic was on mute. Okay, sorry. Uh, okay. So would you like? I think you have understood till here, right? Okay. So I'll take that as yes. Okay. So what we do is let's integrate it. Integrate integrate over the over integrate just integrate on both sides. So we'll have y is equal to 1 plus c1 by 2 into minus 1 by x plus some new constant c2. Okay. And just it's nothing but y of x is equal to minus 1 plus c1 by 2 into x c2. Now let's leave our boundary condition, so to speak. And at x is equal to minus 1, y is equal to 1. So then this implies that, so this implies that, so then this implies that 1 is equal to, or likewise we'll just have minus 1 plus c1 at 2 into minus 1. So it is, so this is nothing but 2 plus c2 is equal to, come on. So it is 1, isn't it? And then this implies that we'll multiply throughout by 2, such that we have 1 plus c1 plus 2c2 is equal to 2. And this we can write in c1 plus 2c2 is equal to 1. So this is our first equation. And the second is that x is equal to 2, y is equal to 4. Okay. So this implies that, so then this implies that 1 plus c1 minus divided by 2 into 2, which is 4, plus c2 is equal to 4. Okay. And we'll multiply throughout by 4. So we'll have minus 1 minus c1 plus 4c2 is equal to 16. And we'll just rearrange it in rearrange to give us minus c1 plus 4c2 is equal to 17. Okay. Now yes, what we do is we simply add both of them, both equations. So we add both these equations to give us, so add both. I'll call it equation 1. This is equation 2. Add 1 and 2. Then this gives us c1 cancels out. So we are left with 6c1, sorry, 6c2 is equal to 18. And then this implies that c2 is equal to 3. And from the first equation, we have c1 plus 6 is equal to 1. And this implies that c1 is equal to minus 5. So essentially, our extremal is y of x is equal to minus Uh, so C2 is already we have as 3, and C1 is minus 1 is plus minus 4, and which multiplies with minus is minus it's plus 4. So it is nothing but 2 by x and then plus 3. So this is our very first problem, which is simple. But now let's move to more complex problems. The second question in this sequence is, so we have to find the curves for which the functional, which is I is equal to 0 to x1, and the function the integrand of this functional is f dx with y0 is equal to 0, and it can have extrema if the point x1 and y1 can vary along the line y is equal to x minus 5. So clearly what's
Sir,
is
the
very much
question
apparent
not
from our
visible.
problem. Not yet.
Second question, sir.
Uh, cannot be visible because either there is some transmission
Variable
delay
boundary
in the.
point. The page which I'm saying is variable boundary point general case page.
Okay. So let me just reshare it. It looks like there is too much of network issue today. Share screen, start broadcast. Uh, how about now?
Yes. No, it is fine.
Okay. Okay. So let me repeat the question in brief. So what we are asked to do here is we have to find the curve for which this functional I with one point fixed, which is y at 0 is equal to 0, and it can have extrema if the other endpoint, which is x1, can vary but along a line y is equal to x minus 1. So very obviously this problem is one where we need to invoke the transversality condition, right? Because one of the endpoint is allowed to move, but it's constrained to move only along a particular curve, and which happens in this case, which happens to be a line. Okay, so
Uh, Sir,
what
this
I do
limit
is,
is for x,
yeah,
no?
yeah, yeah,
This
for
limit
x,
is for
but
x, no, 0 to x1.
yeah, 0 to x1, but x1 is not. It's we don't know it beforehand. It's a variable. So x1 here is not fixed. So essentially, we have some functional which connects, and this happens to be a straight line y is equal to x minus 5. So this was our x naught y naught, which is nothing but origin, and the second is x1, and this x1 y1 is allowed to vary, but only particular curve, which in this case is a line. Okay, let me first jot down the integrand of the functional. So f of x y prime is nothing but root over 1 plus y prime square divided by y. Okay, so very clearly this function doesn't contain x, so it's independent of x. So we can just use our Beltrami identity. It's independent of x. So independent in the sense it's explicitly independent, although you know that it's explicitly independent of x. Yeah. So we use Beltrami identity. So which says that y prime del f by del y prime minus f is equal to some constant c. Okay, and let's substitute our
Hello,
the
sir.
values of the derivatives here. Yeah.
Sir, screen again stop.
Yeah. Oh, I think the internet in this side is slow. I think it's taking time to propagate.
So, sir, better
It's
keep
taking.
refreshing. After every 1 minute, keep refreshing.
Okay, okay, yeah, it looks like I have to do have something like that. Okay, it seems that yeah, it is really slow. Yeah,
Uh, Audio is fine, but this what you are writing, I can't say. It is just still only question is written over there. The solution part is
still
not
frozen.
visible.
Oh,
Yes.
it's still frozen. Okay, okay, it's still frozen. Okay, let me just stop presenting and let me share the screen again. Okay, and share again. Um, okay. Uh, I think it's still loading, right? Still, okay, let me do something about this. Okay, how is it visible now? Screen
Another few seconds it will take.
now. Now? Not yet.
Sir, just asking, sir, you are in Karnataka or
Yeah.
Maharashtra now? Like some music is going on now. That Holika Dahan.
Me? Yeah,
Actually,
yeah,
just
yeah. I cannot help it. No, I
okay.
mean,
Today's Holika Dahan, sir, 7:30.
yeah.
That temple festival will going on,
Sorry?
chanting and all. Very good
Right, right,
music.
yeah.
Super, sir.
So I think, where are you? Where are you exactly?
I'm in Delhi now, sir.
Which?
O-
Okay, okay.
Okay, sir. We'll proceed at the end.
Yeah, so okay. Yeah, I think this internet happens to be a problem. Please let me know if the speed freezes again because it looks like there is some problem with internet. Okay, please just keep on reminding me if. Okay, so let's take off del f by del y prime as is nothing but. um, so I'll write the expression is y prime by root over 1 plus y prime squared with a y before. And will f is nothing but y plus y prime squared divided by y is equal to c. Okay, and let's what we do is let's and in Beltrami identity I'll just mention beforehand that this is h is equal to constant and h is our Hamiltonian. Okay, so what we have here is y prime squared. So I will take 1 by y 1 plus y prime. I mean, I'll just take 1 by y as a common factor. And then we have y prime squared. And then we take LCM as 1 by root over 1 plus y prime square. And then we have this gone. Come on. Okay. Okay. So we have this one as minus 1 minus y prime squared is equal to constant. Okay. So essentially, what this leads us to 1 by y and so here y prime squared cancels out. So we'll have minus 1 by y root over 1 plus y prime squared is equal to c. And so this is also our expression for h. I'll just keep it h here because we require it later. And let's make some more adjustments here. What we can do is uh, what we can do here is let's take negative on the other side. So to say 1 by root over, 1 by y into root over 1 plus y prime squared is equal to constant. And I'll just use the same constant to make any new transformations that I do because that's just to keep on inventing new constants. Invert it, take the reciprocal on both sides, and I'll still keep it as I'll still keep the reciprocal as c. And let's again square both sides. So at both sides, what we have is y squared 1 plus y prime squared is equal to, it should be c squared, but I'll still keep it as c. Now what we do is we'll take 1 plus y prime squared is equal to c by y squared. And this implies that y prime squared is equal to c minus 1. And I'll take this on the next slide. Okay, so what we do is on the next slide, so we have y prime squared is equal to c by y squared minus 1 is nothing but c minus y squared by y squared. And now I'll take square root on both sides. Take square root. And then this gives us y prime is equal to plus minus of root over c minus y squared by y. First, just y prime to be the positives. Let's first consider the positive square root part. Okay. So I'll take the positive square root now. And so this gives us, so this is y prime is equal to root over c minus y squared by y. Now we'll use again our separation of variable technique. So
Sir,
this will give us,
a screen again.
yeah, it's still frozen.
Yeah, now just frozen.
Still frozen, right?
Yes.
Okay. I don't know how to amend this, but let me do something. Uh, actually, I'm using a hotspot today. The screen still frozen. Please let me know. Still frozen, huh? Okay, let me just unshare and share it again. Let me unshare and share it again. Share screen. Start broadcast. Okay. Okay. Okay.
Yes,
I
sir.
think it's going to be frozen.
Now fine.
Okay. So okay. Yeah. Please just keep on reminding if there is any screen freeze again. Okay. So we'll use the separation of variable technique such that we have y dy divided by root over c minus y squared is equal to dx. When we now what we do is to solve this integral, we need to do some substitution technique. Otherwise, it's tough to solve in its current form. So what we do is we have say z is equal to c minus y squared, and differentiating it on both sides, we'll have dx is equal to minus 2y dy, and then this gives us say y dy is equal to minus dz by 2. I'll just try to readable
Sir,
form.
we are changing to
So
constant coefficient.
no, essentially what I'm trying to do is look,
Correct,
this
sir.
z is still a variable. Yeah. So we are essentially just trying to reduce the complexity of the integral of this. This is not solvable in the current form right now. or if even if there is, I think that will be much more complex. So it's better to go for with substitution of variables. So I took z is equal to c minus y square, and then we have this form in such that our we are able to express our y dy in terms of dz. So eventually, what happens is this integrand has now become this integrand has now become or the yeah this integrand has become minus dz by 2 into root over z is equal to dy. We integrate on both sides, and this will give us say minus 1/2, and then z to the power half divided by half is equal to x plus c2. And what we see clearly here is we can cancel out half, or this 2 cancels with the other 2. So we'll have this, and so this gives us minus z square root of z is equal to x plus c2. And uh, and substitute in the expression for z, and then we'll have minus c minus y squared, and half to the power half is equal to x plus c2. And now what we do is we'll square on the both sides, and this gives us c minus y squared is equal to x plus c2 whole square. Okay, isn't it? So, and what we have is we have 2 constants here, and the constants are, so we have 2 constants. C and C2. And when we just review our question again, then it tells us that the, the condition at x is equal to 0 is given as 0. So which means we can use that condition to at least determine, and the other constant has to be determined using our transversality condition. Okay. So what I'll do here is, so now what I'll do is I will just what I'll do is I will put the value here, which says x is equal to 0 and y is equal to 0. So put x is equal to 0 and y is equal to 0. So then this gives us c is equal to, or c minus 0 is equal to 0 plus c2 whole square. So this is nothing. C is equal to c2 square. So we have determined one relation between the constants. So we were unable to get the actual expression for the constant, but at least we found a relationship between both the constants. Okay, so I'll just put this into our expression here, and then we'll have c2 squared minus y squared is equal to x plus c2 whole squared. And then what I do is let's take this implies that we will take let's expand on both sides. So it is on the right hand side, I mean. So on the right hand side, we'll have x squared plus 2c2x plus c2 squared. And we clearly see that we can cancel our c2 squared from both these sides. So we'll have c2 squared 1 and c2 squared 1. And then we will have y squared is equal to minus 2c2x minus x squared. So therefore, y is equal to, again, we can have 2 expressions plus minus. And it is, and what I'll do is I'll take minus 2c2x minus x squared. So essentially, this is the, we now need to determine the expression for C2. So C2 needs to be determined. C2 needs to be found. So I'll start with. I'll start with the. What we do is, so we are given the curve, right? We are given
Sir,
that
screen once again
endpoint.
refresh.
Yeah, yeah. Okay, it's frozen again. Um, Stop presenting and let me present it again. Okay. So you'll be facing this issue only this week. So I'm really sorry for this. uh,
Sir, it's fine. Sir, yeah, just
where does
asking.
that text gone?
You are in North Karnataka or near Kolhapur, Solapur, Maharashtra, or in Madhya Pradesh?
I'm in Bihar.
अरे सर, तो your name is there कृष्णा अवतार जी यार. अच्छा, बिहार.
Yeah.
Okay, okay.
Yeah.
Okay, okay, sir.
Okay, okay. So, okay, so we are given that the end condition, which is x1 comma y1, uh, can only vary along this line y is equal to x plus x minus 5. So we are given that end condition varies along y is equal to x minus 5. So let's just parameterize this curve. Parameterize the curve as in terms of some xi. Okay, so the coordinate, I mean the vector at every point defining this curve. So which means that the coordinates of the curve, I'll just call the curve as gamma, consistent with what was discussed in the lecture. So it's called capital gamma. So the coordinates of the curve is given by small gamma vector in terms of xi is equal to. Now, now you'll notice something that let me just in this curve, let's take x to be the independent variable and call it xi. So let xi be the parameter for with parameter corresponding to x. So it means that y is can be just expressed as xi minus 5. So this is essentially our parameterization. And when we take, so then this implies that d of xi and dy xi is nothing but 1 comma 1, because when we differentiate both the curves with respect to xi, it just leads to 1 and 1. Okay, let's go. I mean, now let's invoke our transversality condition. Transversality condition. So the transversality condition was P into the minus h dx by dz is equal at x1 is equal to 0. So now let's substitute expressions for P and. So for P is nothing but del f by del y prime, right? So P is del f by del y prime, and del f by del prime was expression here. Let's copy this. So P here is this expression here, and dy by dz is nothing but into 1. Likewise, minus of h, and h as I had said that just need to keep this in mind. So this was our h, and paste it here. And what we see is minus into 1, minus into minus 1.
Sir, screen.
It just frozen again. Okay, let me.
Yes, now fine.
Oh, it's okay. No, it's fine. Okay. It happens on both hands, it looks like. I'll just close and start it again. So we are here. So minus into minus is just plus. And then and again dx by dz is 1 is equal to 0. So what we get from here is, then this implies that now mind that y in 1 plus y prime, this is always greater than 1, or at least to the very least equal to 1. And also we are assuming y to not be 0 everywhere, or because we don't want a trivial solution. So it simply means that we'll have y prime plus 1 divided by 1 plus y prime squared is equal to 0. And this we can just take the denominator to the right hand side, and then we'll just have y prime plus 1 is equal to 0. And this has to hold at x1. So our condition at x is equal to x1. Now when we take a look at our curve, I'll just copy the curve, the expression for the curve from here. Copy. Okay, and I'll take the curve from expression from the curve. Okay, come. Just I think it was counterproductive. So let me just write. Okay. So y prime is equal to, so minus 2 here. So I'll just take it as uh, plus minus 1, 1 by 2 into 1 by 2 into minus 2c2x minus x square, and then the integral within, I mean the derivative of the quantity under the square root. So we'll have minus 2 of c2 minus 2 of x. And what I'll take is, for now let's only consider the positive square root of this quantity. Okay. Have so this gives us minus 2 is also as a common factor for the numerator. So then we'll just have minus c2 plus x divided by root over minus 2c2x minus x squared. This is y prime of x. Only considering the positive square root of that particular part of that quantity. So then this implies that what we see from here is, we'll just put it here as C2, and this, since this y prime is evaluated x is equal to x1, we'll just put x1 throughout, and then this is equal to minus 2c2 x minus x squared is equal to, and I'll go a step further, just call it to be at x is equal to x1 is equal to minus 1. And what you clearly see is this minus and this minus cancels out. So we'll have just the positive. So we'll have this quantity here, c2 plus x by root minus c2x minus x. Okay, but see is the transversality condition gives us just one equation, but there are two variables. The variables are c2 and x1. So we need to use
Sir, screen
the
frozen.
very the I mean the okay. Okay.
Sir, yeah. Where you are in Bihar, sir? Patna or where?
It's around 400 kilometers from Patna.
Which place, sir?
It's a district called Supol.
Super. Okay, bordering Nepal. Okay, great, sir.
Yeah. So it seems
And
the
sir, your
internet is
hometown,
weak
sir.
today.
Sir, your hometown, just ask.
Yeah, this is my hometown. Yeah, I just came for a few days.
Sir, but your name seems like a Kannadiga name, na?
Come on.
Krishna Avatar ji, yaar.
Yeah, this is a query I often hear.
So, sir, your full name, sir, Krishna Avatar
Yeah,
ji, yaar. Your complete name, sir?
yeah. So G and R stands for Gauri Ranjan.
Okay, अच्छा, okay, Ranjan Mahoday ji. Okay, Mahoday. Nice.
Okay. So this I'll just note it down here that there are two equations, one equation and two variables. So we needed to use one more condition, which is not explicitly given, but what we call as continuity condition, or also we can just call it as nothing. It's nothing but point of intersection. Same thing. It stands for the same thing. So which means that if we take a look at the curve, right? So the x1, y1 of the extremal, the coordinates of that particular point of the end point of the extremal should be the same as the coordinate which lies on this line here. So what I mean to say here is x1 comma y1 of the extremal should be the same as x gamma y gamma at x1. So this is what I mean. So the point on the line should be the same as the end point of the extremal. So what I do is let's take we'll have x1 comma and y1 we already have. The expression here is, or the expression for y is root or minus 2c2 minus x square, right? So I'll just take it as I had mentioned. We'll be taking first the positive part. So it is minus c2 of x into x minus x squared, and this all at x is equal to x1. And this is equal to an x gamma is nothing but again x gamma is the same as x1. So I'll just call it x1. Gamma at x is equal to x1 is x1 minus 5. Right? And now what we see, since both the set of coordinates are equal, so this implies that we'll have minus 2c2x1 minus x1 squared to x1 minus 5. Okay, so we have obtained one more equation, and the other equation was here. Now what we see, we observe we observe something here, that there is a square root term in this equation, and then that is equal to a very simple expression, which is x1 minus 5. So why do we not just replace the square root term with the simple expression? So we'll call this equation let's just call it as 1, and this has 2. So put 2 in 1, and this gives us c2 plus x1 divided by x1 minus 5 is equal to 1, right? And this implies that c2 plus x1 is equal to x1 minus 5. X1 cancels on both sides, and then have c2 is equal to minus 5. And I'm sure that was the only constant that we had actually to find it in order to obtain the extremal to our problem, right? And so So we need to just substitute the value for C2. So therefore, the extremal is y of x equal to plus minus root over, and 2 into minus 5 is, sorry, minus 2 into minus 5 is 10 x minus x squared. So this was our solution. Okay. Now building on the previous solution, okay, if I'll just list on the steps that we followed, because that's very important when we solve problems with transversality condition. So first we solve our Euler-Lagrange equation, and then we reduce it. We arrive till the point where we are actually able to obtain the extremal in terms of the independent variable along the constants. Then our aim is to obtain the constants. So if we are given endpoints, then we'll use the endpoints to determine at least one constant. Or if we are unable to get the expression for the constant, at least we are able to find the relationship between the constants. Then we employ our transversality condition to obtain the condition for the second constant. And what you'll see is you won't be able to obtain the expression for the constant at one go. So then we just need to use the thing about the point of intersection of the extremal as well as the constraint equation, along with the one of the endpoints has to move along, and then we are able to obtain our extremals. So this is a general procedure for solving problems with transversality condition. Now, building on this problem, what we do is we have the same functional in the third problem, which is find the curves for which the functional is the same. The end condition is also the same. One of the end condition is the same, which is y of 0 is equal to 0. And however, the other endpoint can vary along the circle. So in the previous question, it was allowed the endpoint was allowed only to move along a line. Now we are constrained to move along a circle. So what we do is, let's pick up everything till here. So till here would be the same, because we are essentially solving same problem but with just a different constraint. So I'll just put solution steps till here, steps, or just follow the steps. The previous answer, or in the solution to the previous question. Previous question till it's not okay. So till here we are required to. Okay. So till here we are required to. We have the same goal. Now what we do is let's again parameterize our curve. Parameterize the curve gamma. Now you'll ask, okay, the curve is minus 9 whole squared plus y squared is equal to 9. What we do is let's divide throughout by 9. Just our goal is just to obtain a very simple expression to this problem. I mean a very simple parameterizing. So what we do is we'll divide throughout by 9. This gives us uh, x minus 9 divided by 3 whole squared plus y by 3 whole square is equal to 1. Use the well-known trigonometric condition, which is cos square, say xi is equal plus sine square xi is equal to 1. Okay. So essentially, our coordinates on this curve is nothing x. Then you'll say, okay, so our goal is nothing but to find x minus 9 by 3 is equal to cos xi, and y by 3 is equal to sine xi. Okay, so x is nothing. X will have the parameterization as 3 cosine xi plus 9, and y is a simple is just 3 into sine xi. Okay, so we invoke our transversality condition, which was t into t by d xi minus h into dx by d xi at x1 is equal to 0. And the p, which was nothing, it was y prime by root over y into 1 plus y prime squared. And dy by d xi is uh, okay. Um, okay. So yeah. So this we can just write this quantity as again. I think my goal in this question was to also explain you that how come this two versions of the relation, which one is beneficial at which point of time, right? So I think that was my aim here. So let me not repeat the previous the what do you call the the steps that I followed in the previous question. Let me just make it a bit different. So my goal here was uh, so here what we can do is we can just use the other version of the transversality condition, which was minus h comma p into 1 comma xi is equal to 0 at x. Right? Okay, this was our aim. So uh, uh, so then this implies that we'll just express of x. It is not. It is plus minus uh, root over 9 minus x minus 9 whole square. Okay. So here the transversality condition gives us into so by dx, right? So it is p into dy by dx, and dy by dx is we'll take the positive root again, take positive root of this quantity. So we'll have uh, 1 by 2 to root over 9 minus x minus 9 whole square dot this and again the derivative of the term within the square root. So we'll have minus 2 into x minus 9. And the other term is as we had as we'll have plus because minus into minus plus and y into root over 1 plus y prime squared into 1 is equal to 0. Okay. And so what we do here is, and the other, and this y prime is follows from our, uh, this y prime follows from this quantity term. So that we'll write it as, uh, and then what we'll do is, following the previous case, we'll just take out the common as y into 1 plus root over 1 prime. So this I'll just call it as, and this minus 2, 1 to this goes away. This term, this, and this cancels out. So we will have, then this implies that y prime into y prime into y prime into minus x minus 3, okay, and root over 9 minus x minus 9 whole square, okay, and then what we do is we'll have plus 1 is equal to 0, and then this implies that from the previous from this expression here, we'll have y prime is equal to, taking just the square root, we had minus c2 plus x divided by root over minus 2 c2x minus x squared, okay, and then we'll utilize that here. So it is minus c2 plus x, and mind you that this condition was for at x is equal to x1. So wherever we have x, we'll replace it with x1, and then divided by, then it was divided by, so, and this is divided by minus 2c2 x minus x squared into, and minus into minus, so it's plus, or okay, so okay, let me just I think it's loading. Okay, yes. I'm sorry for the background noise. Let it reload. Okay, we were at slide number 17, I believe. Okay, 16. Okay, and then minus. Okay, so we'll have minus x minus 3 by root over 9 minus x minus 9 whole square plus 1 is equal to 0. And yeah, so and then what we do here is we can take this minus. Let's take this minus, and then on the other side. So I hope you are able to follow along. So it's just equal to 1. So this is okay. So again, what you see is, and wherever x, will just substitute x1. Okay. So so then this simple as that. Again, we just have one equation and two variables, right? So you'll ask me, okay, we'll follow the same step in the previous case. We'll again determine one more equation using our point of intersection. Point of intersection. And so for this, we'll have x1, comma y1. This is equal to x gamma, y gamma at x1, right? And so what we see here is x1 is, we'll have fine, x1 is there. And y1 was for the curve case. So it was for the curve we had, we are taking the root. So it is a minus c2 x1 minus x1 squared. And this is equal to x gamma. So x gamma is the same at x is equal to 1 is the same as x1. And y gamma at x is equal to 1 is this particular equation, right? This is the equation. So we'll take the positive root, and this gives us root over 9 minus x1 minus 9 whole square, right? And then what we do is we balance, or we equate both the terms, both the coordinates on both the sides. So x1 is already equated. For y, let's equate. So we'll have this implies that, and let's also just square it. So we'll have minus e to x1 minus x1 squared is equal to 9 minus, and we'll expand this also. So it's x1 squared plus 18x1 and minus 81, right? Okay, so what we do here is uh, minus x1 square minus x1 cancels on from both the sides, and we are left with 9 minus 81 is minus 72, and so we have minus 2c2x1 is equal to 18x1 minus 72, and then we just cancel out. What we do is cancel out 2 from both the sides. So we'll have minus c2 is equal to, and also divide throughout by x1. So it is minus c2 is equal to 18. So 18 becomes 9, and this divide by x1 is just 9, and minus 36 by x1, right? So we have two equations uh, and two equations and two variables. So it's our additional equation. Okay, additional equation. And mind one more thing. Let me just tell me. This term is equal to this term. So we can clearly see something here, that why don't we replace uh, uh, why don't we replace this term with a more manageable this term, right? So, and I'll again, let's name it as equation 1 and equation 2, and an intermediate equation which is this as well. I'll just call it 2, and this has 3. Okay. 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 So from 1 and 2, we have minus C2 plus X1 into X1 minus 3, right? And then this is equal to minus X1 minus 9 whole squared. And let's just expand both these equations. So we'll have minus C2 of X1 plus 3C2. I think it's not X1 minus 3. Okay, let me just check. There is some miss. Okay, it's X1 minus 9. Sorry for the mistake. Yeah, there is X1 minus 9. Okay, so plus 9C2 and minus X1 squared and plus 9x1. And on this side, we have 9 minus x1 squared plus x1 minus 81. So minus x1 squared cancels out. And then we are left with minus c2x1 and plus 9c2 is equal to 9x1 minus 81. Okay. Now let's subtraction for minus c2x1. This I'll just make something, just divide throughout and still keep that term. So minus c2x1 is equal to 9x1 minus 36. So I'll use this term, this expression here. So it is minus C2x1 is 9x1 minus 36. It's 9x1 minus 36. Okay. And then for 9C2, and mind you that we had expressed the term in terms of minus C1, minus C2, right? So this is nothing but minus, and then we'll have 9 minus 36 x1, 9 minus 36 by x1. And this is equal to 9x1 minus 81. Okay. So this implies that we'll have 9x1. So we'll have 9x1 minus 36 minus 1 plus 9 into 36 by 80 by x1. And this is equal to 9x1 minus 81. Okay, so we are able to spot a few cancellations. This cancels out, this cancels out, this cancels out, and this cancels out. So all we are left with is, uh, okay, I think there is, okay, this is 9, yeah, sorry. So there is 9 plus 9x1, okay, plus 9x1. Okay, so now what we see is 9 into 36 by x1 is equal to 9 plus 36 is equal to 45. So then this implies that 9 cancels out. So it gives us 36 by x1 is equal to 5. And then this implies that x1 is equal to 36 by 5. Okay, so why not we use x1 to obtain the expression for C2? So we'll have minus, put x1 in 3. And this gives us minus C2 is equal to 9. It's 9 minus 36 by 5. And this is nothing but 9 minus 4, and it is equal to 4. So minus C is equal to 4. Minus C2 is equal to 4. So therefore, the extremal is, when we take a look here, it's plus minus 2 into C2 of x. So minus C2 is 4. So it's y of x is equal to plus minus 2 into 4 is 8. It's 8x minus x squared. So these are extremal. Okay. So I think what we do is I'll there is one more problem here. I think we have discussed few problems, quite a bit of problems in transversality condition. I think let's just skip to the one with broken extremals, and if we have we'll return to the transversality condition. Actually, our equation and the questions for transversality got started long back. Just cut here and paste. It was, yeah, in this slide. Transversality. Okay, let's first talk about problems, and then if we have time, then we would return to solving questions with transversality condition. So let us start with the first question in broken extremals. So the question asks us to minimize the function j of y is equal to minus 1 to 1 x2 by x to the power 2 by 3 into y prime square, subject to the end conditions y at minus 1 is equal to minus 1 and y at 1 is equal to 1. So we clearly notice from the solution, from the boundary conditions, that there is both endpoints for both x naught, x1 are fixed, as well as y of x naught and y of x1 are also fixed. So this very much simplifies our problem. So we determine the Euler-Lagrange equations. So the Euler-Lagrange, and I'll take the functional as the integrand of the functional as f. So we'll have t by dx of del f by del y prime minus del f by del y is equal to 0. And so this gives us, again, the same thing. So this f doesn't contain any term explicitly in y. So this is 0. So we'll have del f by del y constant c. And then this implies that del f by del y prime is 2 into y prime into x to the power by 3. This is equal to c. And then dividing both sides by 2, and I'll still retain the constant as c itself. So we'll have y prime is equal to c into x to the power minus 2 by 3. Okay. Now let's integrate it. Integrate. We'll just have dy is equal to c into x minus 2 by 3 into dx. Integrating gives us y is equal to c into x 1 by 3 divided by 1 by 3 plus one more constant c1. And this implies that y is equal to, again, I'll just call, so this becomes 3c1, right? And this becomes 3c1. 3c actually, so I'll just call it c itself. So x 1 by 3 plus c1. So we need to determine the constant c and c1 using our end conditions. So at x is equal to minus 1, y is equal to minus 1. This implies that minus 1 is equal to c into x to the power minus x to the power 1 by 3, or at x is equal to minus 1, it's still minus 1. So it's minus c plus c1. And at x is equal to 1, y is equal to 1. And then this gives us 1 is equal to plus c and plus c1. Adding this gives us 0 is equal to 0 plus 2c1. This implies that c1 is equal to 0. Therefore, c is equal to 1. Therefore, our extremal is x to the power 1 by 3. Now, there is one caveat here. Although we are able to obtain the solution, but still what we see is dy by dx at x is equal to x to, is equal to 1 by 3 into x to the power minus 2 by 3. What we see here is this dy by dx is not a finite value at x is equal to 0. So y prime at x is equal to 0 is tends to infinity. So which means that we don't have a continuous, or we have a continuous function, but it's not a smooth function. So it has a corner at x is equal to 0. However, to solve this problem, we did not require any corner conditions. So that was the main goal of taking up this problem. Go to another problem where we require to use the corner conditions, or the Weierstrass-Erdmann problem. Okay. So the problem asks us to find the extremals of the functional j of y is equal to 0 to 4 y prime minus 1 whole square into y prime plus 1 whole square dx. And the end conditions are y at 0 is equal to 0 and y at 4 is equal to 2. And the extremals has to be one with just one corner. So let's first let's first express or write down our integrand of the function. So f is equal to y prime minus 1 whole squared y prime plus 1 whole square. Okay. And so this problem doesn't have this problem doesn't have any equation, sorry, any term containing y explicitly, and even there is no term even containing x. But still, let's just use this Beltrami identity. So in this case, we y and y prime is equal to some constant c. So h is given here as uh, or so I think that will make a bit life a bit so let me not longer step it. Things won't be very much evident as we'll come to know later. I'll tell you about that. Let's use our Lagrange equation. So dy by dx of del f by del y prime minus del f by del y is equal to 0. So it doesn't contain it in y explicitly, so this is 0. And this implies that del f by del y prime is equal to some constant c. So therefore, del y by del y prime is let's use the chain rule. So you'll have 2 into y minus into y prime plus 1 whole square plus 2 into y prime minus 1 whole square into y prime plus 1 is equal to constant. And then this gives us this gives us we'll take 2 as common and have y prime minus 1 into y prime plus 1 into y prime plus 1. Similarly, y prime minus 1, y prime minus 1, y prime plus 1 is equal to c. This is just to let you know, I mean, this is some trick that we are trying to use. So y minus this you know very well, it's of the form a minus b and a plus b into a plus b. So this is 2 into y prime squared minus 1, and this is y prime plus 1, and this is again we'll have 2 into y prime minus 1, and then y prime squared minus 1 is equal to constant. Now we take 2 into y prime square minus 1 as constant. So we'll have 2 in as a common factor. So it's y prime squared minus 1 into y prime plus 1 and plus y prime minus 1 is equal to constant. So this gives us 4 into y prime squared minus 1. And this minus 1 cancels out. So we'll have 4 y prime is equal to constant. So this let's store, and then again let's miss what you call abused notation. We'll have y prime into y prime squared minus 1 is equal to constant c. So this is our equation that we are going to use further. Okay. So what we do is so the c. Now here c is a constant, right? So it can be either 0 or non-zero. Let's start with the simplest case. Take c is equal to 0. And this is the only condition we'll need to use. Because the moment we take c to be non-zero, then this leads us to solving y prime in terms of as a, so it becomes a cubic polynomial in y prime. And it doesn't have any very straightforward answer. So we just take c is equal to 0. So we'll have y prime into y prime squared minus 1 is equal to 0. So this means that either y prime is equal to 0 or y prime squared y prime squared is equal to 1, and then this gives us y prime is equal to this or condition plus minus 1. Okay, so far so good. And in this case, what we can do is why not take y prime, integrate it once. Integrate it once. I mean, yeah, once, and then we'll have plus minus x plus some constant. Say I'll just call it small d. Okay. So far so good. Now what we need to do is let's use our corner conditions or Weierstrass demand condition. So that states that, so we can have, let me make a schematic of the problem. So our problem is essentially that our endpoints are 0 and 4. So 0 and 4. And the conditions are that y at 0 is equal to 0 and y at equal to 4 is equal to 2. So this is 0 and this is y at, this is x equal to 4 and there is 0, this is x axis. And we need to find using one corner. Let's take this to be the corner. And let's function, and this is also some arbitrary function. And this is our corner conditions x star. So essentially, our problem is to determine the corner condition or the corner formed x star. For this, we and then the extremal for the first interval, which is from 0 to x star, is y1, and the extremal for the second interval is y2. So to in order to obtain the value for the corner point, let's invoke the corner points, which state that the momentum at what we call momentum due to y1 at x star has to be equal to momentum of due to y2 at x star, and the other condition states that I'll add both this side by side. This helps us to visualize it clearly. Okay. So I'll take it here and then so P, okay, so P is del F by del Y prime, right? And with that, we had clearly seen that it effectively uh, becomes, this is our expression for P, right? Because it's nothing but del F by del Y prime. So it is, we'll have 4 Y1 star, sorry, Y1 prime, and then Y1 prime squared minus 1. This is at X star, and likewise for Y2 prime, y2 prime squared minus 1. Canceling out, let's cancel out y prime, sorry, 4 from both the ends. So we will have y prime and y1 prime squared minus 1 is equal to y2 prime. And y2 squared minus 1. Okay. So we clearly see that this term is always going to be equal. And because both the terms is always going to evaluate to 0. Why? Because either we have y prime is equal to 0 or y prime squared is equal to 1. So even if you if you have y1 prime is equal to 0 and say y2 prime squared is equal to 1, in that case, you clearly see that because now let me just state it more clearly. So y of x here is nothing but some constant, say e. And you know very clearly from this here that y of x is equal to e. It simply means that, so if we have, and we have the two boundary conditions that y of 0 is equal to 0 and y at 4 is equal to 2. So if you put, say, since this is a constant and it has also to satisfy the boundary conditions, so let's say this is the extremal for this extremal y1, then e will simply evaluate to 0. And then what we see is and y2 is also of this form as y prime is equal to 0 and such that y2 x is equal to e, then in that case it has to satisfy this endpoint. So essentially there is a mismatch in the sense that it will be from 0 to x star, this is this, and from the other side it is 2 and this is 0. So there is a discontinuity in the solution. So which simply means that we cannot have this condition anywhere. This is not possible. And since we are required to just take one corner point, so either one of that has, at least one of that has to have this condition, at least one of the extremals, either y1 or y2. So what we, so in the sense that it's now very clear that this will always be of 0 is equal to 0 form. So this 0 is equal to 0 always. So it means the first condition is already satisfied. It doesn't give us any good conclusion, but at least it's the extreme is satisfied. The momentum equality condition. Now let's have the second condition, which is y h is equal to. Let me first derive the expression for minus f is equal to now y prime, and del f by del y prime was 4y prime y 4y prime and y prime squared minus 1, and then we'll have and then even f, right? F, what we can do is f, if we'll take a look at it clearly, this we can also write it as y whole square, isn't it? So I'll just write it here as this was nothing but y1 y y prime squared, actually y prime squared minus 1 and whole squared. Now we'll take y, and we'll take y prime squared minus 1 as a common factor, and then we'll have 4y squared minus y prime squared plus 1. So this gives us y prime minus 1 into 3y prime squared plus 1. Now take a look at this equation clearly. H is this part of H is always greater than 1, greater or equal to 1 at the least. At the least it's equal to 1. Now let's from the equality, from the corner condition, we have H at x star, H at say y due to y1 uh, y1 prime at x star is equal to H at y of y2 prime. This has to be equal to at x is equal to x star. So condition 1, condition 2. So then this implies that uh, I hope the expressions are right. Uh, okay, so we'll have y prime squared minus 1 into 1 into 3 squared plus 1 is equal to y2 prime squared minus 1 into 3 y2 prime squared plus 1. Okay, and then let us bring both the terms on one side and also expand it. So we'll have, say, y1 prime squared minus 1, and also I'll take it on the next slide. This looks very clumsy. Right. And then paste it here. Okay. Mm, okay. Yes. So what we do is okay. So we need to okay. Okay. So we'll have y1 square minus 1 into 3 y1 prime squared plus y1 prime squared minus 1. And then likewise, we'll have y1 y2 prime squared minus 1 to 3y2 prime squared plus prime squared minus 1. Okay. So this gives us so this gives us 3 into y1 primes to the power 4 minus 3y1 prime squared plus uh, y1 prime squared minus 1, and this is equal to y1 primes 2 is 3 to the power 4 minus 3y2 prime squared plus y2 prime squared minus 1. And then this evaluates to 3 into y1 prime 4 minus y2 prime 4. And this becomes minus 2 y prime squared, and this is minus 2 y2 prime. So we'll have minus 2 y1. This cancels out, so we'll have minus 2. We'll have minus 2 y prime squared minus y2 prime squared is equal to 0. So we'll take it out this as a factor, and this gives us 3 into y1 prime squared plus time squared, and minus 2 is equal to 0, isn't it? Now for this to hold always, we must have y1 prime okay. So either this has to be 0 or this has to be 0. But the thing is, from the very condition that what we had seen is y prime is equal to 1 or y prime is equal to 0, right? So from both the cases, it looks like this term is never going to be 0, isn't it? So the only other possibility is this has to be equal to 0. So then this implies that our condition simply becomes that y1 prime square is equal to y2 prime squared, and then this gives us y1 prime is equal to plus minus y2 prime. Okay, and we already know the value for y1. So we already know that these are both equal to 1, right? So let's take y2 prime is equal to 1. So then this implies that y1 prime is equal to minus 1, right? So solving this equation, what we have is this implies that y2 prime, y2 of x is equal to, say, some x plus b. And I'll just delete this part. It's not relevant right now, but anyway, or not for the sake of not confusing, let me call this y plus capital A, and this as y1 of x to be minus x plus b. Okay. Now let's determine A and B using endpoint conditions. Endpoint conditions. Okay. So what we have here is so y1 is so these are all linear equations. So we'll have something till here, and then so this is y1, and this is our x star, and this is our something of this sort, yeah. And this is x, or this is x is equal to 4, and this is 0, and this is our y2. Okay, so now we know that y1 of x is equal to minus x plus b, isn't it? Yeah. And now what we clearly say is y1 at x is equal to 0 is 0. So this implies that b is equal to 0. Done. Now y2 of x is equal to x plus a. And we also know that y2 of y2 at x is equal to 4 has to be equal to 2. So this implies that 2 plus a, or otherwise it's actually 4 plus a is equal to 2. So this implies that a is equal to minus 2. So therefore y1 of x is equal to minus x, and y2 of x is equal to x minus 2. Now let's determine our and the corner point using our point of continuity to determine corner point condition actually. So then this implies that minus x star is equal to x star minus 2, and this gives us 2x star is equal to 2, and this gives us x star is equal to 1. So this is our corner point. Corner point. Okay, so essentially our extremal is y is equal to 0 at x is equal to this one is minus x for 0 is less or equal to x less than 1, and then x minus 2 for the case of 1 less than. So this is our extremal with one corner. One corner. So yeah, I think we have exhausted our time. And what I would like you to do is just go through solve these two problems for for the case of transversality condition yourself. And if you're unable to, please let me know in the next tutorial session. So I'll stop the recording here. Yeah, stop presenting. Okay.